This is question 10 from the second CSAT sample paper. Here we're given the curve y equals 12 minus x squared. We draw a tangent to it, which is the equation y equals ax plus b, and we're asked to find a and b in order to minimise the area between this line, the tangent, and the axes. So this triangle here formed by the tangent. So if you want to have a go at this question yourself, pause the video now. Okay, so first things first, what are we going to do? Well, we're probably going to have to differentiate at some point to find a minimum. So we're going to need a formula for the area, but at the moment that formula will rely on both a and b. So there's going to be two unknowns. And we want only one, so we need to find some relationship between them. But the information we have is that this line is tangent to this curve, so it touches this curve. So let's try and relate A and B by writing down the information that they touch at that point. That the line touches the curve at that point. So first of all, the easiest thing to write down is that the line and the curve have the same gradient at that point. What's the gradient of the line? It's just A. What's the gradient of the curve? It's going to be minus 2x, where x is the x-coordinate. So I think the easiest thing to do is to introduce the x-coordinate as a new unknown and then relate it to both a and b. So let's call alpha the x-coordinate of the point of intersection. And then from the gradients being the same, we have a equals minus 2 alpha. And from the fact they intersect, we just put alpha into both equations. A times alpha plus b is 12 minus alpha squared. And now if I rearrange this to get b, I can get b in terms of either a or alpha. It doesn't matter which. So I'm actually going to get it all in terms of alpha rather than a, just because it means I don't have to divide by 2. It means I get rid of fractions. And then I get minus 2 alpha squared here, so I just move that across and I get 12 plus alpha squared for b. So now I could, again, write this in terms of a, but I'd have fractions, so I prefer not to. We can keep everything in terms of alpha, because at least now that's our only variable. So now if we find the area, it can be put in terms of alpha, and then we can differentiate with respect to alpha, and we'll still find a minimum. So what is the area? Well, if we draw this curve, the y-intercept is b, and the x-intercept is minus b over a. If we have ax plus b and y is 0, then x has to be minus b over a. And that means this length here is b over a. Minus b over a. Bear in mind that a is negative, so this is a positive number. And this height here is b. And the area is just a half height times base. So that's a half times b times minus b over a, which is b squared over minus 2a. Again, this is positive because a is going to be negative because it's slanting this way. So now let's put this all in terms of alpha. So b was 12 plus alpha squared, so on the top I'm getting this squared, and on the bottom just minus 2 times this. So on the top we get 144 plus 24 alpha squared plus alpha to the 4. And on the bottom we're getting minus 2 times this is 4 times alpha. And if I'm going to differentiate, I think it's easiest to divide 4 alpha into each of these terms. So when we divide 4 alpha into 144, 144 over 4 is 36, and then we have 1 over alpha is alpha to the minus 1, just for ease of differentiating. Here we get 6 alpha, and here we get a quarter alpha cubed. And now we want to differentiate. So I'm differentiating from this end, so I'm putting the larger powers first. When we differentiate this, we bring down to 3, go to alpha squared, so 3 quarters alpha squared. This just goes to 6. This goes to minus 36 over alpha squared, because alpha to the minus 1 goes to minus alpha to the minus 2. So this is our derivative. So we need to set this equal to 0, see what alpha is, and then calculate a and b from that. So we'll do that on the next page. Okay, so here's our derivative, and we're setting this equal to 0, but first let's get it in a nicer form. So we can put it all over alpha squared or 4 alpha squared. We can also take out a factor of 3, so I think it's easiest to take out a factor of 3 over 4 alpha squared. And if we take that out, we have a quartic inside, but it's basically a hidden quadratic. So we get alpha to the 4 from here, and then 4/3 times 6 is 8 times alpha squared, and then 4/3 times 6 is 48. So this is the inside. And now it would be nice if we could factorise this, because then it's easy to set equal to 0. Bear in mind alpha is positive, because in the question we were told x is between 0 and root 12. So we're looking at the right hand side of the quadratic that looks like this, and it starts at x equals 0 and then it reaches the x-axis at x equals root 12. So we're just looking for alpha to be positive. So this is not going to be a problem. We just want to factorise this and hope we can get a root. And it turns out this does factorise. It factorises to alpha squared plus 12, alpha squared minus 4. And now this bracket is never going to be 0 because it's alpha squared is at least 0 and this is positive. But we can have alpha squared equals 4 from here, so alpha is plus or minus 2. We want it positive, so we want alpha equals 2. So for a turning point, the only possibility is alpha equals 2, because alpha is positive. And if alpha is equal to 2, if you plugged it into our formula for A and B, A was minus 2 alpha, so that's 2, and B was 12 plus alpha squared, which is now 16. So these are our values for A and B. We might just quickly worry about this being a minimum rather than a maximum. But it's worth noting that our picture looked like this. So how big can the area be between the tangent and the axes? Well, if the tangent touches very close to the y-axis, it will look like this, and you'll get a very large area. So as alpha tends to 0, the area is tending to infinity, and if it touches very close to the other end, you'll get a similar thing. As alpha tends to root 12, again the area is tending to infinity because this line is going vertical. So therefore the area gets very big at either end, and so if there's a turning point in the middle, it has to be a minimum. It has to be the smallest value between these very large values at either end. So we can be confident that this is a minimum.